Hi, everybody. We'll get started here in about 10 minutes. Thanks for your patience. So we'll get started here in just about 5 minutes or so. You'll have to bear with me this morning. I'm at a conference and I'm trying to connect my Bluetooth so you can, so we can have a quiet kind of audio stream. But I'm working on that. So bear with me. Okay, everybody, thanks for your patience. We'll go ahead and get started. Let me go ahead and share my screen. So as a reminder, we don't have lab class today for those of you who are in lab with me. We covered everything on Tuesday, and I will make that recording available to you here shortly. I have it. I just forgot to post it in the announcement section, but it will be there here shortly. So on Tuesday, we started our discussion of two-dimensional motion. We looked at the requirements for projectiles, meaning that as far as the projectile motion goes, the horizontal motion has no acceleration, while the vertical motion of the projectile is being controlled by gravity. And so we looked at the resources that you have available, the free fall pyramid and the acceleration, velocity, and time pyramid for the horizontal motion. And with the acceleration for horizontal motion being 0 in that pyramid, and the acceleration being gravity for the vertical motion of the projectile. Because while each of those is happening at the same time, they are independent of each other. And then we went on to look at circular motion. And we looked at an object moving, for example, in an orbit, having an acceleration toward the center of that circular path, simply because the object is moving in a circle and changing its direction at all times. And so what I wanted to do today is to look at some sample problems for you. Now, with projectiles, to be honest, we don't really solve too many problems with that. We looked at the range formula, and that's about the extent of it. Sorry, everybody. Sorry. I'm right outside of a conference that I'm attending, so if it gets a little loud, I do apologize for that. But you know, I can't control how loud folk are getting. I'll just try to talk a little louder for you. So if you go into our extra resources that are posted in the announcements, and I'm going to go into the link for all of the folder notes, and I have some really good examples for you and information on 2D motion that you can take a look at. Okay. But what I want to jump into is this example of circular motion for you. Okay. So on Tuesday, we looked at an example of circular motion. We looked at orbit motion, and in particular, I used the satellite as my example. And so what I'm going to do today is to look at two different types of satellites and use the formulas that we learned on Tuesday for uniform circular motion. Remember, that is motion where the object is going around in a circle with a fixed speed, but an acceleration because its direction always changes. Okay. And so I'm going to solve two problems for you here that look at, for those two different types of satellites that are orbiting around the Earth, which one of them is actually going faster. Okay. So the two types of satellites that I'm going to focus on, one is called a geosynchronous orbit satellite, and one is called a low Earth orbit satellite. I'm going to look at the parameters for each one of those and then use those parameters to help us determine which one is going faster, right? So the first example is a GEO, and that is a geosynchronous orbit satellite. And what it means is that it rotates around the Earth once every day. So basically it stays above a fixed point on the Earth's surface and follows the Earth as it makes its daily, daily cycle of 24 hours. And on Tuesday, we talked about the idea that the time that it takes an object to make a complete circle, in its orbit is called a period. And so for this satellite, this GEO satellite, because it makes one trip every, once a day, just like the Earth does, it has a period of 24 hours, okay? And this geosynchronous satellite is approximately 22,000 miles out above the Earth's surface. They operate in that region, and these numbers are, since they're, this is a pretty substantial distance, I kind of just rounded it off. So that's approximate, okay? And so because it's 22,000 miles above the Earth's surface, it's actually about 26,000 miles from the center of the Earth. Because if you think about a circle, well, the way a circle operates is it has a center, and every point on a circle is the same distance from that center. And when you look at orbit motion, you have to pick the center of that circular orbit, okay? And of course, we talked about that on Tuesday, that, for like planets and what have you, we're approximating their orbit to be a circle when actually most planets have that elliptical type orbit. But for this satellite, since it's actually orbiting around the Earth, we, to use a circular path is a really good approximation of the motion. Okay, so the parameters that we're working with for this GEO is that it has a period of 24 hours and it has an orbit radius of 26,000 miles from the center of the Earth. Okay. And so we'll use those parameters to help us figure out the tangential speed. Recall, I told you on Tuesday, you'll see different terms being used for the speed of that of the object that's orbiting or making a circular path. Some books will refer to it as tangential speed. Some will say, they'll just say speed. So you just have to be comfortable with the various terminologies, all meaning the same thing for this object that's moving in a circle, okay? And so we're gonna figure out how fast it's going, the speed, and then we're gonna figure out how big is this acceleration that it's feeling, right? Because remember, because it's going in a circle, it automatically is getting accelerated toward the center of that circle, all right? So now let's use that period and radius in our speed formula. Well, that means you have to go back and remember, what is speed? Well, it's distance divided by time, right? And so the distance in this case is the circumference. One trip around is the circumference, 2 pi r. That's going back and knowing the formulas for a circle, right? Circumference, 2 pi r, area, pi r squared. We don't want the pi r squared. We want the circumference, which is the distance around once, okay? And then we have to divide that distance, by the period, because we need distance divided by time. And the time in this case is the period T, capital T. That's the symbol that we use, right? So when we plug in our numbers, 2 pi, which we use 3.14, and then the orbit radius, 26,000 miles. So we're multiplying all that. And then we're dividing by the period, 24 hours. So I did this in miles per hour because I know that for most of you, if you drive or, been in a car before, this idea of miles per hour is probably more familiar to you for a problem like this, because we're trying to gauge based on our own experience how fast this thing is moving, right? I could do it in meters per second, but that might not mean as much to you because I'm trying to get you to visualize what this orbit motion is looking like. And so when you multiply and divide, multiply all the top numbers and divide by 24, you get 6,803 miles per hour. And I round it off there, okay? I round it off to the nearest, ones place if you want to, get technical about it. So 6,803 miles per hour. Now, we have to put something behind that to help us understand exactly what does that mean. Well, it means this satellite is out there orbiting, this geostationary satellite, and is covering 6,800, miles every hour. That's what miles per hour means, right? And 1 hour is going to go roughly 6,800 miles. I mean, that's a pretty incredible speed for an object to be orbiting around the Earth, when you really kind of think about it. I mean, think about the fastest automobile that we have can't touch that. You want to think about it in terms of everyday motion that you are probably, really familiar with, a car, right? So now that we know how fast this geostationary or geosynchronous satellite is moving, we can use that to help us figure out the centripetal acceleration. Recall that to get centripetal acceleration, we looked at that formula on Tuesday. You have to take the speed squared and divide by the orbit radius, right? So take the 6,803 miles per hour, square that whole thing, and then divide by 26,000 miles, all right? So that means you're squaring on the top part in the numerator, you're squaring the number as well as the unit, okay? So when you finish the top part, you're going to, make sure that you account for the whole unit being squared. But then remember, you're dividing by 26,000 miles in the denominator. So one of your miles is going to cancel out. The number, you square 6,803 and then divide that by 26,000 and you'll get 1,780 miles per hour squared. And again, I round it off because we're trying to approximate here, right? We don't have to be spot on to get an idea of which one is going faster in this case, right? So that's a fairly nice sized acceleration for this object being accelerated toward the center. Now you might ask the question, well, if it's if it's having such substantial acceleration toward the center, think about it. This satellite is orbiting around the Earth, and it has this acceleration toward the Earth. It's being accelerated toward the center of the Earth. Why doesn't this crash and burn into the Earth, right? I mean, that seems like a reasonable question. If the acceleration is that big, excuse me, why doesn't it just accelerate right toward the Earth and burn up? Well, you have to remember that it has an extremely large forward or tangential speed or velocity that's is keeping it in that orbit, right? So if to think about it, if that's a satellite, if it's got some kind of motor or engine or whatever it is that's providing that that speed for it, it has to be able to maintain that. Otherwise, if it doesn't maintain that tangential speed, it will crash and burn. Okay, and that you think about it, that's the same thing for the Earth going around the sun. As the Earth is going around the sun, it has to maintain its forward velocity, this tangential velocity at all times, or it will start to spiral into the sun. You think about it, what is keeping it out there going around the sun? That's gravity, right? So if somebody, miraculously finds the gravity switch and turns gravity off, then the Earth will go spiraling into the sun, and a whole lot of other things for that matter, right? So, that whole tangential velocity, tangential speed is critical for it to maintain that orbit, all right? So now we see what's happening for the Geo. Let's take a look at the Leo. And, the Leo is one of what I guess, I'm kind of I really enjoy this notion of satellite motion because, in my mind, we use satellites for so many different things nowadays. Communication, um, you know, got some spy satellites going on, um, you know, uh, all kinds of things out there. But the one that I'm most like impressed with or um, interested in, if you want to say, is the International Space Station, right? And I'm not sure if all of you know about it, but there's actually a satellite out there. It's called a low Earth orbit satellite, or sometimes you hear it said near Earth orbit satellite. That satellite is out there orbiting the Earth, every day, and there are people actually living out there on it, and there are people out there doing all kinds of scientific work. You might have seen on the news sometimes where folks actually communicate with the astronauts that are out there on the International Space Station. People send supplies, via SpaceX and there are all kinds of experiments going on, because one of the things we've got to figure out if we're going to transition from Earth to other planets and other places in our universe is how to exist out there. And the International Space Station is a cooperative effort between the countries of the world to help figure that out. Okay, because if the human species is gonna survive, then we increase those chances when we become when we live on multiple planets. Because if something happens and Earth gets destroyed, and we're not somewhere else, then just kind of like the dinosaurs, we'll get wiped out, right? So they're thinking about those kinds of things when they when they're out there doing this type of research. And so people are living out there for a substantial amount of time, which is phenomenal when you think about it. We have learned how to transition from being a totally terrestrial Earth species to actually being able to live out in outer space, at least for some portion of time, right? That's pretty incredible, right? When you think about it. And so this International Space Station is what we call a low Earth orbit satellite. And so it makes a trip around the Earth once every 90 minutes. Okay, so an hour and a half, right? 1.5 hours. It makes a complete trip around the Earth. Okay, so that's his period is 1.5 hours. And since it's in what we call the low Earth orbit, it is not nearly as far out as the Geosynchronous satellite. That satellite is about 26,000 miles from the Earth center. This satellite is about 100 miles above the Earth's surface. And again, I'm approximating, which means it has an orbit radius of about 4,060 miles from the center of the Earth. Okay. And so we can use those parameters, 1.5 hours as the period, 4,060 miles as the orbit radius, to help us figure out the tangential speed and centripetal acceleration. Okay, so we go right back to those same formulas: distance over time, right? Speed is distance over time, 2 pi r over t. So plug in 2 times pi, 3.14 times 4,060, our orbit radius, and divide by the period, 1.5 hours. So again, when you do that calculation in miles per hour, 16,998 miles per hour. And I round it. You could round that off roughly to 17,000 miles per hour, right? If you wanted to, just have a real rounded figure there. 16,998 miles per hour. So again, think about what that means. This satellite that's orbiting the Earth about 100 miles out from the surface, and you can actually see it on some nights, depending on where it's at. It is making a trip around the Earth once every 90 minutes, and it's covering 16,998, or roughly 17,000 miles every hour. That is a phenomenal speed for an object to be out there orbiting around the Earth. with people on it. Okay. And now, so if it's out there going that fast, how much is it being accelerated toward the center of the earth? So take that speed, 16,998 miles per hour, square the whole thing, and then divide by 4,060. And you get 71,166 miles per hour squared, again, rounded. So you can kind of process this two ways. This object has to go very fast to counteract that large acceleration toward the center so that it doesn't spiral into the earth. Or you could think about, because it's going so fast, is producing, you know, that large acceleration toward the center of the earth. But in any event, the Leo wins hands down because it's going about what, about 2.5 times faster than the Geo satellite that's out there. Okay. But notice what I did. I took the parameters relevant for each satellite, and I used them in those two formulas that we looked at on Tuesday. One to get the speed, the other to use the speed to get the acceleration. Okay. And that's the kind of thing I would expect you to be able to do regarding orbit motion. Okay, to utilize those two formulas to adequately and quantitatively describe the motion of an object that's moving in a circle. Okay. Now, as far as our projectiles go, well, let me stop here and ask, what are your questions about this particular example that I've worked? Again, I do apologize for the talking in the background. Hopefully you can still hear me okay. All right. So again, as I mentioned, there are some great notes out here on projectiles. I will go back and just kind of we'll take a quick look at two different types of projectiles. So let me see if I can shrink this down a little bit. Okay, maybe you can, I didn't even do that. Okay, maybe you can see that a little bit better now. So one type of projectile that I want to focus on is called a symmetric projectile. Okay, and symmetric means that if I take the path of the projectile and cut it in half, it'll take the same amount of time to rise or reach its peak as it does to fall from its peak, right? So it takes the same amount of time going up and coming down. And that's because its path is symmetric, meaning it starts and stops at the same height. Okay. Now, I don't expect you to solve any problems related to that. We don't even, you know, that's a concept thing. Even though I wrote it out here in a formula, you can really think about it this way. If it's symmetric, the time to rise equal the time to fall, or if you know the total time, you just cut it in half and you'll know either the time to rise or the time to fall, right? Because it's even on both sides, okay? And the only other thing that, you know, you really might want, you need to know for this type of projectile is this range formula. Recall on Tuesday, I talked about the idea of knowing the range for a projectile because we know that the horizontal velocity does not change. So that makes that calculation the only one I expect you to do regarding a projectile very straightforward. Okay, the range for a projectile, you take that horizontal velocity, which is fixed, and you multiply it times the total time. Please do not mix up the formulas for a projectile with the formulas for circular motion. There are two different types of 2D motion. So that's a very basic calculation for a for the range, because if you think about it, distance equals speed times time. Okay, and that's all we're doing. We're using that relationship. Okay. The other type of projectile that you will come across is called a non-symmetric projectile. Well, if it's non-symmetric, what we need to know is what it's not going to take the same amount of time to rise and fall. And it's not going to be even on both sides. And so, again, though, the calculation that I would expect you to understand is the one, here, that deals with the horizontal range. So you see here, this is the range formula for a non-symmetric projectile. And what you notice immediately is that it doesn't matter whether the projectile is symmetric or non-symmetric, you find a range the same way, same formula. Okay. And so that's a kind of a calculation that I would expect that you would be able to do. Okay, for a projectile. It's symmetric, it takes the same amount of time to rise and fall, and finding the range. Other than that, to know that the horizontal acceleration for a projectile is 0. And that means that the acceleration that a projectile feels is on its vertical motion due to gravity, right? But, you have access to all this good information on projectiles and circular motion in the extra notes that I provide for you. Remember, you can always reach those in the announcements. Okay. All right. So with that, I'm going to stop my share. And again, I thank you for your patience this morning and your attention, because I know, I'm kind of in a little bit of a distracted environment. Hopefully that didn't cause too much grief. So if you have questions, please feel free to unmute and ask your questions. I'm happy to address any of them.
No,
I didn't catch that. Are you asking me a question, Nikki?
I said no, ma'am. I don't have any. I said no, ma'am.
Yeah. Well, it kind of broke up a little bit there when the audio on my side is. I'm sure it's because I'm using the Wi-Fi connection at the hotel where I'm at this conference, and sometimes that's not, it's not the greatest. But hopefully y'all were able to follow along with me this morning. So if there aren't any questions, we're done for today. Bear with me. I will get those recordings out there. I'm a little bit slow, but it's because I've been driving for the past 8-9 hours, and I really didn't have much time to do things on my computer because I didn't have a Wi-Fi until now. So I'll get that out there for you. No lab today, and we'll be back at it again next Tuesday. No, hey, I forgot. This Tuesday coming up is Mardi Gras, right? So I have to go back and make sure that I fix the schedule. If I schedule anything for Tuesday coming up, it's not going to happen because we don't have class. So what I really need for you to do more than anything this, in the next couple of days is really check Canvas and check the announcements, because I might have to do some finagling with the schedule. Because at the time, maybe when I planned this class, I might not have taken into account Mardi Gras, and so I've got to go back and take a look at that. Okay, but I'll post something in the announcements for you to make sure we're all on track and know what's happening next week. Other than that, I really appreciate y'all being patient with me today. Have a good one.
Thank you. You too.
Take care. Hi, Jonathan. Do you have a question for me this morning? Jonathan? We're actually done, Jonathan.
Yeah, I know. I'm sorry. My computer's been really laggy the entire time. Like,
Well, hopefully, the playback on the video will be sufficient if there are some things that, you know, you want to go back and review. Did you have any questions for me this morning?
yeah,
You kind of broke up on that. Can you chat? I can check the chat if you had a question. So we're all done this morning, Jonathan. If you have a question, I'll be checking the chat. I'm not sure if you're able to chat, but if not, how about you shoot me an email and I'll be happy to respond to any question that you have that way. That might go smoother.